Hi friends, welcome to our channel GL Qubit Minds. So in this session we'll discuss on quantum computing, quantum gates. So this is our video 3. Let's get started. Okay, so here we'll know what is tensor product and why we are doing. So when we want to multiply multiple qubits like 0 and 1, we need to multiply with this help of tensor product. So basically tensor product describes the joint state of the system. So we use a symbol, this cross sign inside a circle, we call it tensor product symbol. So if we want to do multiply of xi and phi, so we use this tensor product symbol, or we can use this kind of symbol also, it's fine with the this sign, and this phi and comma and xi and comma and phi also it's fine. So this kind of way we can write a tensor product of multiple qubits. So we have seen that the basis state, suppose is xi equal to alpha 0 ket and beta 1 ket, we can represent vector of this coefficient alpha and beta, where alpha and beta is complex number coefficient. Okay, so here now we are going to see what happens when we are going to multiply, what is the rule, how it multiplies for the two qubits in a tensor product. So if 0 and 1 we know already, 1 and 0 is represent, this is a column vector, it signifies this 0 ket, and for 1 is 0 1. So when we are multiplying, you can see it is multiplying in a different way. So this is the main vector, so for each element it is multiplying with the second qubit, second vector. So 1 into 0 1 and 0 into 1. Okay, I will just 1 minute here, there's a laser. So here it is 0 into 0 1 and 1 into 0 1. So when you are multiplying these two, so it is 0 1 and 0 0. So here you can see 0 1 0 1 0 0 is the final output. Now if so, we all know that 0 0 0 1 1 0 1 1. So this kind of output we can get. Here we can see it is 0 1 means this one. So if you want to represent in the vector, so it will be first one is 0, then 1, then 0 and 0. So this will be our vector representation. So it is correctly we have multiplied, so this is the outcome. Now for multi-qubit state we can come to a generic statement. If A is a coefficient of 0 ket, A 0 ket, B is 1 ket, we want to do a tensor multiplication here with the C 0 ket and D 1 ket. So we have to transform it, we have seen it here like this, we have to transform this into vector A and B and C and D, then we will do the tensor product. So like this same approach we will follow. A will remain as it is, B will remain as it is, and each element of A we have to multiply the whole second vector, and with B with the second vector element. So now this will be the output, A into C, A into D, B into C, B into D. Okay, now we'll see, this is, we know that this is a superposition. So how do we come to know it is a superposition? Because this is 1 by root 2 and this is also 1 by root 2. Why? Because if you want to get the probability will be alpha square and it will be beta square. So if alpha square is the probability, then we will get 1 by 2. So it is 50-50 chance to get these two state. But you can also see this is also called a entangled Bell state. what is entanglement. So here I will now see. So also we have to note that a superposition state collapses into a classical state based on the associated probabilities. Okay, well, now we have to understand what is the phenomenon of entanglement. Entanglement is a broader concept that includes Bell states but also other forms of quantum correlations. Means basically, if you want to say that what is the entanglement concept, is that means the qubit are correlated in such a way that the state of one qubit is directly tied to the state of other qubit regardless of the distance. Wherever we want to keep it, there will be correlation of between two qubits. If that is the case of between two qubits, then we can say it is both the qubits are entangled to each other. And Bell state is one of the example of entangled state. Okay, there could be G H Z also. It is also a entanglement state, entangled state. Okay, so this is a very important in quantum computing, entanglement. So in this state we will see the Bell state. A Bell state is a specific type of quantum state involving two qubits that are maximally entangled, and Bell state are inseparable. You cannot separate with any tensor product. You cannot represent with a tensor product. So but the tensor if any qubits can be represented by a tensor product of two separable qubits produces without entanglement, means there is no entanglement between two qubits if it is separable. Okay, so this this state, Bell state, has been used in several quantum information theory and quantum cryptography and quantum computing. Also in teleportation cryptography also Bell state has been used. So there are four Bell state. You can see this is the one 0011 by root 2. If it is minus, this is 5 plus 5 minus, xi plus xi minus. This is all the four Bell state. We cannot represent using a tensor product. Okay, now we'll see how the gates actually operates. So we'll in the next slide we'll see different kinds of gates. Before that we need to understand what is this gate actually. So when we'll like in our normal digital world, we have seen that there are several gates like AND gate, OR gate. So here also we'll see different kind of quantum gates, poly X gate, poly Y gate, Z gate, all those things we'll see. So but what is the logic, how it operates? So basically in quantum computing, each quantum gate is represent a unitary matrix. It is very important term. So it is represent as a unitary matrix, ensuring that the transformation preserves the total probability norm of the quantum state. So this is also very important. So when we are multiplying a unitary matrix with a input quantum bit, it should preserve the probability, means if the probability will be alpha square plus beta square should be equal to 1 always. So after the multiplication also it will follow this probability. And if suppose this is phi 1, if we multiply this with a unitary matrix, so unitary matrix will see each gate represent a different unitary matrix. So poly X gate, poly Y gate, all the matrices are different, and if you multiply it we will get a output another new state, or we can call it new state vector also, we can say it. Suppose in a generic way, if we say we have a system of n qubits and we are using a gate of 2 to the power n by 2 to the power n unitary matrix. Here if you multiply with a vector 2 to the power n dimensional complex vector, then we'll get a new state. Okay, new vector state. So basically I want to try to say that every gate has its own unitary matrix. Now this unitary matrix should satisfy few norms. So if we multiply unitary matrix with a unitary matrix dagger means the conjugate transpose or Hermitian matrix, then we'll get a identity matrix. Both unitary matrix dagger into unitary matrix also same. Also it will also follow this, if the unitary matrix dagger we have, then it will be equal to the inverse of unitary matrix. Okay. Now in our previous session we have seen that the Bloch sphere. Just I am to recap it a little bit. So this Bloch sphere actually a representation of a qubit. So if you want to represent where the qubit is, we can represent in we can just a graphical represent or geometrical representation of a qubit. Okay, so here we can see this is 0 1, this is x y, and this is the different coordinates. So here the polar coordinates theta. So this is the theta coordinate. So this polar coordinate controls the probability distribution between 0 and 1. So what is the probability that it should be 0 or it should be 1? And there is a azimuthal angle, this is the phi. So this will denote how it will rotate in the xy plane, and the theta will represent this angle, means how much probability, what is the chance it will be 0 or what is the chance it will be 1. Now okay, now we can move to next slide. So now we come to our the important slide is quantum gates. Okay, so quantum gates are the fundamental building blocks of a quantum circuits. So now we'll see single qubit gates. Our first gate is, so this is just a few list of quantum gates, there are many more. So poly I gate, we can also call it as a identity gate. So this is the symbol represented in the quantum circuit. So the matrix, we have already told there is a unitary matrix. So for if you 2 by 2 matrix, so we can see one in the diagonal path, everything will be 1, rest it will be 0. So if we give an input here, if we give a xi here qubit, we will get the same xi as a output. So there will be no change.